Okay, hi everyone. So I'm going to talk today about some of the new features of the neural network framework in version 12. So basically, it includes everything we had it since version 11, 11.0, and which means a lot of things because the neural network were pretty new in 11, so it was quite of a it was an experimental project. It is still an experimental project. But at first there was only basically, convolution networks and fully connected network, like these sort of things to work well on images, but it wasn't working for text. It wasn't, there's many missing things that we had it since. So there's been a lot of new layers, new encoders, decoders that have been added. So the one major point is that it can handle sequential data, such as text or audio. It actually does it pretty well. You don't have to pad text. That's one of the. I don't think there's many frameworks that have that. So neural network framework usually like to be given tensors, right? So non-ragged array. And so text, since it's variable length, you often need to pad this text that, let's say, all your texts are the same size, and you can give it to the framework. It's not the case in our framework. You just give text as text, and it just work. And we do some sort of binning inside and so on. That's not it's not important. Another main thing we added is the model repository. So, sort of model zoo where we have about 100 networks, and it's still growing, including some very recent ones. So it's critical to use neural networks. It's pretty rare nowadays that you start your project by crafting a network from scratch. Usually you take a network from a repository and then you modify it, and then you fine tune it to your application. And I'm going to show things like this. We actually have a nice way to modify networks that we call our net surgery function. I will talk about that. And then, of course, final thing we did is trying to improve the performance using the latest libraries. So it uses MXNet on the back end, but sometimes we need to plug in like an extra library to accelerate on a given hardware, because this can run on CPU, on GPU, and it runs on many different types of hardware, and we want it to be as fast as possible on each of these, and including the possibility to have multiple graphic cards. That's something fairly recent. Okay, so this is a product page that maybe you look you looked at already, and that's basically going the basis of this presentation. I'm going to basically explain what's in this product page, show some examples, maybe evaluate some examples. We'll see, probably. So this shows some typical, some examples to showcase what's new in version 12. All right. So the first row is about the models. So, for example, how to access things from the repository. Anyway, how to modify a network, how to fine-tune it, like this sort of things. Second row is about new architecture that you can do in the framework. Third row is about some applications. So it's just example of application in audio, in text. So each network has its own page. So you can see a little bit how to get the network in the language. You have information also about what it is, where it comes from, a training set. Often there's a paper associated, so we mention it as well, and what you can do with it. So that's a bit what the repository is. So actually, let's just do it. Let's imagine that we want to take a network from the repository. For example, this one. It's probably going to take a little bit of time, depending on my connection. Okay, 38 seconds. That's not so bad. And so it's downloading from our repository, from our database. And then you can use it on, let's say, this image. I mean, first we'll have a little look at it. Okay, so it's pretty, I mean, somewhat classic network. What type of network it is actually? It looks like a Inception, maybe. I'm not sure. No. Okay, so okay, this is the net chain, and so it has many. This is kind of, you know, I mean, conceptually, each of these is one layer, but some layer are pretty rich. So this layer is a net graph. So if I click it, I can see the net graph, and it has many layers inside of it. Things like nonlinearity, this is the batch normalization layer, this is the convolution, and so there's a bunch of this net graph that looks a little bit similar than pooling layer. Okay, that's what this network is, and we can, for example, evaluate it on an input, which is the image. So what you should notice is that it works directly on images. I didn't have to transform this image, you know, to get numbers. And then give it to the network. It works directly on the image, and it could be an image of various dimensions. It would work. This is because of the net encoder, which you can see. Actually, we could grab the encoder. Let's do it. So if I do net extract and input, this is a net encoder that is inside the network. And this, by the way, is one of the surgery functions to manipulate networks. And you can see that it expects an image. The image size is 320 by 320, but it can be another image size. It will just be, resized to the proper size. Even if you give a black and white image, it will still work. It will convert it to RGB. And that's why you can give image directly. And you notice that the output is not probabilities, for example. It's directly the classification. I could ask for the probabilities. And you should see, this should be an association. Oh, it's going to be big, I think. How many image net competition data? Okay, so competition is 1,000 classes. So actually, we could see it here. If we get the output. Okay, this takes time because it has to display this big association, and that's actually messing things up. I'm asking the front end too many things. So let's just cancel that. I'm going to say this is proba. At least it won't have to display it. And okay, so it's already over, and I can say, let's look at the top probabilities, and it doesn't have to display everything. Top probabilities, it should display like the top. Okay, I mean, it's pretty sure it's alliance. So let's look at the top 10 probabilities. All right, so you see, it could give, okay, these are the probabilities, and this is because of the net decoder. So if I do net extract output, you can see a net decoder and all the labels, and that's also a particularity of this framework, that I have this net encoder, decoder, and so everything is inside the network. You don't need to have some, pre-processing, post-processing code. It's part of this framework. All right, so that was an example. You have other examples. So this one is about coloring an image. This one is about segmenting an image. So basically, finding the set of pixels that belong to a given class. So we can say that, okay, this is the background. There's a cat here. There's a dog here. Dog, cat background. This is another network which is for speech to text. So it's a deep speech 2 network that is trained by Baidu on some English speech. And so you can see how you can just grab the network. I mean, we could have a look at it. Let's try to understand what's inside this deep speech 2. All right, so there's a net map operator with a net chain inside, convolution. Okay, a bunch of batch. Okay, and a bunch of net bidirectional operators. So this is our way. These operators are quite interesting. They're also new in 12. I mean, basically everything is new in 12. This is a very high-level construct to define bidirectional recurrent layers. And so you can put any network inside. So let's look at the documentation. So it's a very simple way. You just net directional operator and you put network inside, and it will apply it. It will so it will apply to a sequence, and so actually probably there should be, what is the input output matrix n by 2, output n by 6. So n is the size of the sequence. And there's similar operators like that. So let's see. Let me show you all the page. So net map operator this is a very simple operator. It's just the function map for neural networks. So let's say you do net map operator of a linear layer. It will apply this linear layer to every every element of the first level independently, and it's actually very, very useful. Actually, depending on the shape of the data, it might be equivalent to a one-by-one convolution, which is used a lot. There was others, net fold operator. Okay, so this is the equivalent of the function fold, but for networks. So it will apply a network. Let's see, it will apply a network to an input, and then apply the network back to the result of this first operation and to a new input. So it's kind of eating the input one by one, but refeeding the outputs of the previous computation in. That's what the fold operation is. A very functional programming approach, very useful. And actually, this framework kind of inherited from the philosophy of the Wolfram language. And one of these philosophical points is to be functional, and which is pretty nice because it's it suits well neural networks to think of it as a functional programming, like in a functional way with a functional paradigm. The other aspect is more the symbolic aspect that has been inherited for the network, and this means that you can manipulate expression. That's really what symbolic means. So this is actually an expression. So it's a bit, okay, there's a bit hidden stuff. So it's not exactly as transparent as the expression you have when you do, 1 plus b. This is an expression like, let's do x times 4. Okay, let's do something like this. Like this expression. So it's really like a native Wolfram language expression. There's a bit of hidden stuff, but you can still manipulate it like other expressions. So I showed net extract. I can show net tag. Actually, I'm going to show it in another example after. So if I say net tag 10, this will take the first 10 layers of the network. And then I could do net join to join to network. I could do net replace to replace some of the layers. There's all this function that makes it nice to grab a network and just, manipulate it. As opposed to finding the source code of a network and in the source code changing stuff. That's not really it's a different way of handling neural networks, which I think is very intuitive. Like you just look at it. It's your network. You have it almost in your hand, and then you can manipulate it, and then you can do stuff with it. Okay, so this is the language model. So basically, it's a network that can predict what's the next character given the history, given the previous characters. All right, and that's a recent, like an BPE. Okay, let's look at another page. So, okay, this one use a pre-trained model to visualize features. So that's one of the things you can do with a pre-trained network. So here we grab a network that's been trained on ImageNet. Okay, so something to recognize images, basically an image classifier. And we just take with NetTag, as I showed before, the first 22 layers. So there's 24 layers for this thing. Let's look at it in the language, in a notebook. It doesn't take too long. Okay, great. So that's a ResNet 50. So 50 represent the depth of the ResNet. It's a wide ResNet. Okay, and you have a bunch of this. Net graph here. You can see the ResNet architecture is really copying the input and then adding the input with the output. And this has been kind of the architecture that allowed to do very deep network they can still train well, and because of that, they got very good result on for image classification. Okay, so that's it, and then we can just take the first 22. So let's take, net and 22, and this will actually work. And then you can use that as a feature extractor. So because let's grab this image and let's show what's happening. Okay, because now there's not the last linear layer softmax, and there's not a decoder anymore. There's no decoder anymore. So let's give it a name, and I'm going to apply it. And here I should see a big. I hope the front end won't be too unhappy. No, that's fine. Now I see just a bunch of numbers, which are basically what was happening at this after the reshape layer. So okay, it's a vector of size 2048 should be for the dimension, or could do length 2048 exactly. And what's nice is that this is these numbers that we call features are semantically rich, because these are the features that are used to determine what's in the image. And so we can use that first to do some, okay, we'll do, maybe I will show some transfer learning after. But one thing we can do is using the feature extractor directly in feature space plot. So basically this, take the image, extract the features that are already semantically rich, and then map that to 2 dimension. And you can see that all the tigers are together, all the bears are together, all the cats are together, and so on. So anyway, that's one way to use a network, just as a feature extractor to visualize. You can also use that as a feature extractor to transfer the knowledge of a network to another network. So that's what this example is about. So actually, it's the same network. You just take up to this convolution layer, and you, with net join, you add back to this, so you cut the head of the network basically, and then you add a new head, which is just a net chain with a linear layer and a softmax and a decoder. Okay, and that's basically the final net, and then you can just train. So this will fine tune your network to this training set. Actually, okay, something important here is that we set the learning rate of the previous network to 0. So it's only learning the end of the network. And this is to prevent the network to forget everything it learned in the beginning. That's one way to do transfer learning. Okay, this is an example that shows a visualization inside. So basically, this is extracting a network, the same thing. This is just extracting the weights and visualize the weights. And so you can understand, at least for the first layers, then it becomes more complicated for the deeper layers. But for the first layers, you can understand, oh, this one is kind of recognizing, like if there's I don't know, let's see. They're all pretty interpretable. So this one is kind of a line on the side like this. This one is, it's mostly like straight line type thing. This is a gradient from blue to red that it can capture. So you can see what they're doing. Let's see what's, okay, that's a bit of a fun with making this network hallucinate. So here the idea is to wonder what input image would activate a given layer, activate the most a given layer, and you can understand. So let's see, this is the inception layer 3B. Like these are the input that activate this layer. So there's another way, instead of looking directly at the weights like we did in the beginning. Sorry, what's happening with my internet? Okay, on my browser. Instead of looking directly at the weight, now we really look at the input image and we try to see what activates a given layer, and that gives you an idea of what this layer is doing. So this layer seems to be, I don't know, recognizing some patch. But this higher level layer kind of recognize, you can see some pose seems to be some sort of animal features that it can find. Okay. Oh, and this one is clearly animal features. I can see eyes. I can see leg. I can see. I don't know what it is, but that's what the job of this layer. I mean, maybe one of its job is to do. Okay, so let's look at the architectures. So this is new architectures. Some are quite exciting. Probably the most important one, because it's very classic. It's recurrent neural net. I already told you a little bit about that. Is that we have this. So let's see. So their network, their layers directly, like long short-term memory layers, more commonly known as LSTM, like things like that, like recurrent gated layer. And you also have the possibility to create a custom recurrent layer with net fold operators. That's really the net fold operator. So let's say here we want to create a multiplicative LSTM. We would create the core. Where is the core? Where is the core? Oh, it's probably in this. Okay. The core is a bit complicated here, but of course, creating a multiplicative LSTM is not. It's not a common layer, by the way. That's why it's not. We don't have a simple construct to do it. So here, okay, you would create the next net graph, and with all its machinery, and then just use a net fold operator, and here you go. That's your multiplicative LSTM. Okay, another important thing is a net state object. This is a construct that allows you to iterate on. So it's not for training. It's when you evaluate a recurrent network. What you might want to do is to evaluate it on a sequence. Then this network produces an output that you feed back to the layer to produce the next step of the sequence. That's what happens, for example, in language model, where you start with hello, then you predict the next character, then you feed all back in you feed. So one way to do would be to feed everything again. So you have hello, then you predict the next character, you just join it with the previous string, and then you feed everything back to the recurrent layer that produces the next character, and so on. But this is very long, because at some point you'll have a very large string that you need to pre-process completely from the beginning. So net state objects allow to not do that, and basically have a memory of the state that the recurrent layer or recurrent network was in, and then you can just give the new input. I mean, basically the prediction of the network, and it will predict the rest very quickly. That's one way to evaluate recurrent network fast. Basically, that's what that is. That's really easy to use as well. So have a look. Transformer neural nets, very important, somewhat recent architecture. We link to the paper. Attention is all you need. That's the image in the paper. And so this architecture is something that works on sequences, a bit like a recurrent layer, but it's not recurrent. It's really a new kind of architecture that is based on self-attention, and that has very good performances on text. And by performance, I don't mean that it is fast. It's not necessarily faster. It can actually be slower. But it's just like, for example, it allows to create language models that are much better than before. It's just better prediction performance than the other architecture for text. And so here we show two examples of this transformer network that are in the repository. So one is GPT, which I forgot what it stands for. The T is probably transformer. Generative pre-training transformer, maybe something like that. Which is a language model. This is a language model. And BERT is not a language model. So this is the more recent. This is something of, so this one of OpenAI, GPT, BERT is Google AI. And BERT gives very good, and both of them give very good features for text. So it can be used as a feature extractor for text. That's really where they shine the most. These two, that's a main function. BERT can only do feature extraction, while GPT can also do. You can also use it as a language model, and the reason for that is, I will come back to what I mean by feature extraction, but the reason for that is that GPT use causal attention, while BERT use, I mean, it's both self-attention, but one is causal and the other one is not causal. And you need causal to be able to generate a sequence. While with self-attention, you cannot generate sequence. So okay, let's. I'm jumping a little bit far here. It's several things I want to say. So what are these feature extraction? Well, basically, let's show it. Huh? So let's grab BERT. Let's say, yeah, let's grab BERT. Let's look at it also. It's a nice network to look at. Actually, one way to understand, for you to understand what BERT is to take the paper or the blog about BERT or about transformers, and on the side, you actually you explore the network like this. And I think doing both is pretty informative. So yeah, it has many net chains, net graph. This is a bunch of these 12 attention heads. And at the very core, the attention layer, which is a generic layer to create attention mechanism in the framework. That's what BERT is. And let's apply it to the cat is on the mat. Let's not do matrix plot. And you will see that there's a bunch of vectors. This is basically a first vector, a second vector. Basically, it's doing one vector for each word. Not necessarily a word. I think in that case, it's for each word. Sometimes it can cut a word in two. It can be a subwords. Most of the time, it's one vector per word. So let's look at the length, actually, or even dimension. You see there are 8 vectors, and each vector is on size 768. 1, 2, 3, 6 words. So one is the vector start of sentence and start of string and the end of string. So there's really one per word. And these words are these vectors, are very rich semantically. I mean, this one is end of sentence, first beginning of sentence. Okay, this one is the vector for the, and it's very rich semantically. It's a representation of the word the, but not like classic word vectors. Classic word vectors, they like word2vec, they don't take the context into account. It's the same representation for all the you can have in a text, while this one will depend on the context. So in this context, that's what the representation of the should be for this network. And that's what makes this network so powerful. I mean, that's the use of this network to have this word representation in context. And the reason they are so good, there's 2 reasons. One is because they have been trained. I mean, one is because it's used a transformer network that is apparently a very good architecture for text. And the other one is that they have been trained on huge corpus. So this one maybe book corpus and English Wikipedia. I think it's about all Wikipedia. I mean, I don't know, but it's a huge corpus. And so they know a lot of things. And nowadays, most state-of-the-art natural language processing application will use BERT as a pre-processing step. So you first reprocess your text with this thing, and then on top of it, you can learn, add additional layers and so on for your particular application and your particular data. So anyway, extremely important network. And what are we showing here? Okay, we show a bit the embedding part. We show a little bit the network, difference between classic self-attention and causal self-attention. This is the other 2 architecture you could use for text: convolution architecture and recurrence architecture. So actually, let's talk a little bit about that to give you an idea what this self-attention is so good. So with convolution, you have this convolution kernel that is moving along the sentence. So basically, in that case, it will be of length 3. It would compute something from the cat and sat, okay, and compute the next step. This one computes something from cat, sat, and on, okay. So it's really just getting information from this from this neighborhood to compute the next step. And if you do many layers, eventually you'll be able to have something that has seen the whole sentence. Okay, the sort of field of view of a given layer will end up being the whole sentence at some point, but it can take time and many layers. Whereas with self-attention, at the next layer, so you can also have several layers of self-attention like that in a transformer. After one layer, you can already see the whole sentence. And that's one of the strengths of self-attention. But it doesn't overfit either, because it's a bit smart in the way it does things. So recurrence is the other approach, where you basically first read the first token, and then you read the second token, and you compute something, and then you compute something with a new token, and so on and so on. So at the end of the first layer, and then you can put another layer on top of it, another layer on top of it. So at the end of the first layer, you already seen the whole sentence, but the problem here is that it needs to, let's say the and mat interact a lot for some reason. In that case, I don't think that's the case, but let's say that to understand this sentence, it's really important to put the and mat in connection very quickly. With a recurrent layer, it's a bit complicated because it might forget what it's seen in the beginning. So that's one of the problem of a recurrent layer. Okay, so all right, so I'm not going to go into details, but basically what we are doing with that is that we're running benchmarks. Okay, so we are fine-tuning GPT and BERT and I think another pre-processing for text on a movie review sentiment task. And the results are that, so GLOVE, this is a classic word vector, okay, no context. We achieve an error rate of 24%. With Elmo, which was one of the first, not the first, but one of the first to have quite powerful, word vectors in context, we achieved 19%, that's better. With GPT, we are 18%, and with BERT, we reached 15%. So BERT is not always the best, but in most cases, BERT is the best. One of the reasons compared to GPT is that it's not constrained to be causal. And anyway. Okay. Let's see the last two. I want to show all of them because it's pretty cool architecture. Okay, that's Capsulenet. That's kind of a new architecture to handle images. So by Jeff Hinton and his group, and so it's kind of an alternative to convolutional neural network. It's a lot in its research phase. I don't think it's used for much application as opposed to convolutional networks that are used everywhere. But it's a pretty interesting architecture because it offers like a bit of a different way to train, to process images. One of the things that it does, so it does several things. Maybe I'm not going to detail everything. One of the things that it does is that it's also, let's say you train on the MNIST digits. Okay. What this model does is not only predicting what this digit is, which is 6, it also predicts, it also, a bit like in an autoencoder, it will also try to reconstruct the original image. Of course, it could just copy the image, but in the architecture, because it has to, it has limited amount of information it can pass through in the middle of the network. Let's actually look at the network. A bit like in an autoencoder, it cannot reconstruct things exactly. So it has to be a little bit smart to understand what the image is. So this, I think, is pretty nice idea, but that's not the other idea. The other idea is a dynamic routing thing. So, all right, okay, well, not an expert on Capsulenet, so I should. Not sure that I can understand. Well, let's see. Primary caps. Convolution. There's still some convolution inside. Reshape. No, that's more dynamic routing. That's important stuff. Okay, anyway, I'm not going to dig too much into it. But yeah, that's one of the ideas to do some construction. And another idea is this dynamic routing that you can read the paper about. It's doing several iterations to compute the next step, and having all the capsule agreeing with each other, the sort of voting system. Anyway, okay. One other thing also we can do is this interpolation. So here we interpolate between 1, 2, 3, and 4. All right, so you can play with it if you want. Self-normalizing neural nets, that's also one of my favorite architecture. It's extremely simple architecture. That's the code to create a self-normalizing net. So just, okay, table. So here we're going to do things of length 7, okay? And we have a linear layer, and then we have this nonlinearity, which is CELU, which is, let's look at it actually. Okay. All right, so that's scale exponential linear unit. That's what this CELU is, and there's probably a documentation about it. Element-wise layer. Yep, that's what this thing is. It looks like this. It's nonlinearity. And it's kind of a magic nonlinearity that if you just have, if you give input that are normalized, meaning each features have a mean of 0 and a standard deviation of 1, and you pass it through this kind of network that has this nonlinearity that's important and linear layers, then it continues to be normalized all through the computation. And this property, I mean, plus a sort of a variation on a dropout layer, which is the alpha dropout method, which is also part of our dropout layer. So it keeps the normalization. And this network is the first neural network. This architecture, the first architecture that allowed to train a neural network on what is it called? Like not text, not image, but structured data, like classic data set. And which is great because in the past neural networks were only used for images and for text, but not really used for structured data. For structured data, you would use let's say random forest or gradient boosted tree or super vector machine or something like that. And these would perform better than neural networks. But it's the first one that competes with super vector machine and random forest and this sort of classic machine learning method. So that's made a bit of a big splash when it got out probably 2 years ago, something like this. And yeah, it's extremely easy to do, and it works pretty well. And actually, because it works so well, the neural network method of the classify and predict function are using self-normalizing neural networks. So if you do method, let's see, method neural network like that, method neural network. So when you do this, actually it's self-normalizing neural network inside. And actually we could look into it. That would be fun. So let's look at the inside of this classifier function. And here you go. You have the net chain inside. And that's, here you go, linear layer, scale exponential. So this is a kind of because it's a very, very simple problem, it shows not very deep network, but it can be deeper. Okay, so that's what it is. Let's continue. Maybe, yeah. An example to train an audio classifier. Okay, great. So I think it uses, let's see, this probably does some transfer learning. Okay, just creating the encoder. Oh no, it is from scratch. Okay, so net bidirectional operator with gated recurrent Learn units. That's the recurrent network that is constructed here that, and then you just use nettrain to train on this. That's kind of the result of what happened with the training. Should show you one train. I mean, the training. I think this one might be a little bit. Let's try. Maybe a little bit slow, but I didn't show you yet what it looks like when you train. So we're going to hop. Or maybe I show that on the other. I'm scared it's going to be slow to train this one. Let's see. Up. Okay, great. No, it's the same thing. Let's create a network. Okay, that's a recurrent layer. Not layer, sorry, recurrent network. I mean, I guess what is a layer, huh? In our thing, a network can become a layer. Okay, you go. That's a training on my poor CPU. So it's not going super fast. I mean, it says that it needs 3 minutes left. I mean, for the default amount of round that has been set. So you can see the loss. You can also see the error rate, which is pretty new. It's because, and it's actually currently quite high, 75%, but it's going down. Because, you know, it figures that there's a softmax at the end, and also because the net decoder is a class decoder, then it understands it's a classifier and understand that we might be interested in seeing the error rate as well. You notice that we didn't set the loss function either. And again, it's because the nettrain understands it's a classifier and it says we didn't specify a loss function. We could if we want to, but because we didn't, it figures, oh, let's use the mean cross entropy loss. We didn't define as well the optimizer. So it used Adam in that case. We didn't define the batch size. We could as well define the batch size as optimizer, but all of these things can be done for you in an automatic way. Which is part of the appeal of our framework, that and be able to visualize things. Okay, so should we stop? Okay, it's still going down, but we don't have that much time, so let's stop it. And we can grab a test data. Okay, that's test data. You probably won't hear. So that's, I mean, I could evaluate. Okay, believe me, it said 9. So now let's try it. Oh, actually, okay, no, that was a 6 example. So let's see if it recognizes a 9. Well, I mean, given the error, it might or it might not, huh? Let's see. 9, yes, great. So it works, and I could actually ask for the probability. So by the way, this is a trained net. So let's just grab it. Net equal trained net. Okay, that's a trained network we have. And a net on this stuff. I could also copy paste this business. And that should be a 9. And let me ask for the top probabilities. And yeah, 80% of chance to be a 9. Top 5 probabilities. Okay, maybe the person said 5 as well. And this is an example of. Oh yeah, that's an example of transfer learning. So you take your resulting network, you just take the 5 layers and use a feature extractor and you use classify directly. Actually, one thing that I'm curious about is what would classify works great on this data set. We could try. And here you just have to do classify and training data. And that's basically what it is. And let's see what's happening. And wait. Oh, right, wait. It's in the right. The training data output 8. So how could we do that? Well, one way, I'm going to grab all the inputs. So this should grab all the audio. Yeah, let's do like this. Up. Inputs and output. Okay, that's one format one of many formats that classifier will understand, because here it doesn't even know what to predict. I just gave it a list of data. So what is wrong with this? Whoop. That is weird. Looks like a bug. So what's happening? Wait, what does this give me? Okay. Okay. I don't see a problem there. I think I just run into a bug. It's embarrassing. Huh. Couldn't it be encoded? Net chain. That's surprising. Okay, well, we won't know how much classify performed. I don't know what's happening. I wonder if I use maybe I messed up and I use a developer version. Okay. Okay, because normally classify does some transfer knowledge inside, so it might be pretty good at this task. Okay, so maybe quickly, this is how you can train a network for language model. Okay, that's for text. So we can see here it's a recurrent network again, and that's how you would set up the training with teacher forcing method, which is really the normal way of training a recurrent autoregressive language model with a recurrent network. All right, and then you can use this net state object. I already talked about that to predict and to do random sample of the language model. Let's show. Let's see. Wait. Segmenting images. Okay, that's be one way to. I think this is using. Yeah. Okay, this is using a pre-trained model, and it's fine-tuning it for learning an image segmentation. I won't detail this example. It's a pretty cool example to train a reinforcement learning. So to train for an agent to learn how to behave in a given environment. This is a super classic control theory environment called simulated car pole or inverse pendulum, and so you create a network for your policy, extremely simple network in that case. Loss. There's a lot of okay. This is not that easy to set up because you have to collect episodes from the environment and so on. We are currently figuring out how we can make that simpler, like some utilities for you to easily collect and run a network in an environment and collect the observation of the network and the reward of the network and be able to train a reinforcement learning agent in a simpler way than that. But at least you can do it. So if you want to start playing around with training reinforcement learning agent with our framework, you can. That's what this example is showing. And hopefully we can make that super simple and it will never be super simple, but more simple. Okay, and so this example are about showing how training on multi-GPU is faster. So this is training on, let's see. Okay, this is one training on 6 CPU. And it's pretty slow. Okay, 15 examples per second only. All right. This is a training with 1 GPU. So now we are 435 examples per second. That's quite better. And this is a training on 4 GPU, which, by the way, is just target device that we change here. Okay. So this, I think it's a machine, it's a server on AWS that we try that on. And you can just say, so by default, we use all the CPUs. And then you can say target device, or first target device. Wait, where is the second? What? Okay, this is trained on the 4th GPU. So only one of the GPUs, the one that is named 4. And this is trained on all GPU, okay? And so, okay, we're 400 and now we are, how much? Okay, yeah, 600. Oh, yeah, actually, it's it's rising. So overall, we're about, or maybe I was wrong with the first one. It's more than, I'm reading 400, but I'm surprised. Okay, I'm actually surprised. Like, this number is higher than what's reported here. Okay, whatever. So arguably you're faster with the GPU. I mean, let's see. Yeah, it's 530 the mean, and here the mean is 200. Huh. Okay, that's interesting. Okay, what's reported here is not what's reported here. I wonder which one is wrong. And probably this one that is wrong here. I don't know why. Okay, it'll be interesting to look at. Or maybe we just messed up with with the video. You can try it yourself. Things to explore training results. So this is a net train results object that when you train with net train, as a third argument, you say result object, and this gives this box. And then the box you can query. You can say loss plot, final plot, and so on, and have a lot of information about what happened. So you can look in documentation, you can do a lot of things. This is another way to get information. You, as a third argument, instead of putting this, training result, result object property, you put an association, and you actually say which property you want. And you can do some plots and things like that. So that's ways to really understand what happened during the training. Okay, this is the bit of extension of classifier measurements, but for any net. So there's net measurements, and you can measure, you can measure accuracy. You can measure. Okay, first training progress measurements. This is something you can give during the training, and you see during the training, I can actually put a confusion matrix. So I think that's pretty cool. You can customize the things you see during the training. Okay, and then net measurement, it's after training. You can ask a bunch of things, including confusion matrix, including other stuff. Like, yeah, what is that? Activation. Anyway, you can look in documentation. There's some cool things you can. Let's have a look. Cool thing you can ask. Okay, this is pretty classic. You can ask the value of given port. Anyway, all right, I'll let you explore this. And let's see, I think we are almost done. Yes, okay, this is something, okay, a little thing to automatically stop the training. So you can have a training stopping criterion, and you can say, like, look at the F1 score, and patience is something that basically will wait 100 steps, and if it didn't improve during this 100 step, then it will stop. So that's one way to define, to kind of, a custom criterion to stop the network, but in rather simple syntax. All right, so I think that's it for what's new in version 12. And I don't know if there's some question coming in, but anyway, don't hesitate to give your opinion, and if you have, if you have ideas on what we should do next, or if there's something you like or don't like, don't hesitate to give us feedback. They are greatly appreciated. And I'm going to stop here. Thank you, everyone. Bye-bye.